Hi everybody. Now we continue on the material balance for the combustion reaction system. Previously we introduced you how about the combustion reaction. With the combustion reaction with the present excess air. Okay, for this case we will consider about the material balance on the combustion reactor. When you draw the first step, you have to draw and label the flow chart, but you ensure that what is the outstream, the gas air. Include the outer stream of the combustion reaction first include unreacted fuel unless you are shown that all the fuel is consumed, right? Unreacted oxygen and water, carbon dioxide as well as carbon monoxide if the problem statement say any in present. And the last one, nitrogen. Nitrogen if the fuel is burned with air, not pure oxygen. So it's mostly the stack gas should be included, right? Unreacted fuel, unreacted oxygen, water, carbon dioxide or carbon monoxide, and the last one it should be nitrogen. This is the most common, the stack gas or the outlet gas after the combustion. Okay, to calculate the oxygen feed rate from a specified percent excess oxygen or percent excess air, what percentage have the same value? Right? So it doesn't matter which one is there. But calculate the first step, you have to calculate the theoretical oxygen required based on the fuel feed rate. Right? So for this calculate based on the chemical reaction of the combustion reaction, based on the stoichiometry after you balance left side and right hand side, right left side and right hand side. Okay, if only one reaction is involved or three balance method, molecular species, atomic species, and extent of reaction are equally convenient. It's up to you. If you would like to molecular species, you can use atomic, you can use or extent of reaction, you can use. Like for the single reaction. If there are several reactions occur simultaneously, I will such like it the combustion to complete reaction or to incomplete reaction. For this case, I infer you that atomic species is convenient. For that case. For this example, right, we burn the ethane. Ethane is C2H6, that's like with 50% excess air. The percentage conversion of ethane is 90% of the ethane burn. 25% react to form CO2 and the balance react to 25% react to CO and the balance react to CO2. What it means is we have at least two chemical reactions. The first one react to be CO. The second one react to be CO2 with 75%. And the question is calculate the molar composition of stack gas based on dry basis and molar ratio of water to dry stack gas. For this case, we have at least two feed. That's right. First step, you balance based on the 100 mole phase ethane. Phase ethane. Okay. And the second one, you have to draw the flow chart and label. Right? The first one, you have two feed. Feed is ethane, 100 mole. And the second one is air. Air is excess with 55% excess. 5% excess air. For air, this we denote as N0. N0 is mole of air. That's right. Mole of air to feed. For this case, mole of air includes 20 mole percent of oxygen and 29% of nitrogen. And then you can denote as the ratio, in the fraction, 0.21 mole oxygen per total mole, or 0.79 mole nitrogen per mole. This is the feed. And the product gas is include unreacted ethane, unreacted oxygen, nitrogen, and product CO, CO2, and water. For this case, we have two reactions. Aside from the problem statement, 25% to CO and 75% to 75% to CO. Okay, the first step, you have to write the chemical reaction. Base it already, flow chart already, and then you write the chemical reaction. For ethane, react with oxygen to be CO2 and water. Okay. The second one is ethane react with oxygen to be CO and water, and then you have to balance left hand side and right hand side. Atomic should be equal. This balance already. I think you can balance by yourself. For this case, there is no proximity mole fraction are no. You can calculate this individually component amount rather than a total amount or mole fraction. For this case, you label as N1, N2, N3, N4, N5, N6. Not state at the completion. The air just like it form the approximately two components in air, oxygen and nitrogen. If ethane react completely in one food me. For this case, if ethane completely, there is no N1, but mole of ethane are not remain in the output because it react completely. But if you okay, we write is N1, but you don't know complete or not. O2 is appear in the output because we access oxygen. Okay, for the material balance calculation, in this case, we assume nitrogen is inert. Nitrogen is inert. There is no reaction because we don't know the temperature. If I comment the last lecture, if the temperature is about 1008, okay, it's maybe nitrogen react to the nitric oxide. For this case, we assume no nitrogen react. There is no problem to NO, NO2, and 2O2 collective. For this case, there is no nitrogen reaction. And then you analyze it of degree of freedom. As the first step, basic, draw the flow chart reaction, and as it of degree of freedom, we have N0 to N6, we have 7 unknown. Instead, we base it on the atomic balance. Okay, 7 unknown. We have 3 atomic balance. Carbon, hydrogen, oxygen. And inert one is nitrogen. And then like the excess, the information is excess air. Excess air is 50% is one information. And also like the ethane conversion. Right? Ethane conversion. 90% is the information. 1, 2. And also the ratio of CO and CO2. 25% CO and 85%. This is the ratio of CO and CO. 3 information, 1 inert and 3 atomic balance. You get 0 degree of freedom. For this case, you can solve by the atomic balance. This is the degree of freedom around the reactor. It's only one reactor, 1 unit. Okay. For this case, you analyze the information. We have 3 information. The first one, 50% excess air. Okay, you can analyze this value, and then you analyze the 90% ethane conversion, right? And 20% convert to CO. These are 3 information. You have to analyze this first. After you analyze, you can solve for some unknown. Okay, for 50% excess air, 50% excess air, what does it mean? You have to calculate the oxygen required due to the theoretically. Please note that I talked to you earlier because the excess or theoretical requirement based on the complete reaction. For this case, you have to calculate the oxygen required due to theoretically based on the first reaction. That's why this complete reaction. Complete reaction. Okay. In this case, the chemical reaction is 1 mole ethane. That's right. Require 7/2 mean 3.5 mole oxygen. This means 1 mole ethane requires 3.5 mole oxygen. But for this system, we feed 100 mole of ethane. We feed 100 mole of methane. Mole of methane is cancelled. You get 350 mole oxygen. This is the mole of oxygen required based on the chemical reaction or theoretically required. Enterically. And for this case, you know, 50% excess air, 50% excess air and 50% excess oxygen is the same. The same. If you talk about the percentage. For this case, if you remember the equation of the percent excess of the you know, right? The percent excess. Show you this. Percent excess equal to it minus vertical divided by vertical. That's right. And then you can calculate like the 0.21 NO. What does it mean? 0.21 NO. 0.21 SO mean feed oxygen. Feed oxygen is 0.21 mole oxygen per 1 mole of total multiplied by NO mole total, you get mole oxygen. This is feed. This feeds oxygen. Is oxygen equal to 1.5 multiplied by mole of oxygen vertically. This comes from this layer. We'll write something for you. Percent yes equal to feed minus equal to vertically. That's right, vertically. Okay, if in the ratio, that's right, you not percent, you not by 100. E EXE. E multiplied by EXE equal to F feed minus vertically. Right. Vertically multiply excess equal to F minus vertically. Okay, you get vertically multiply excess plus vertically equal to F. That's right. This means F equal to, what does it mean? E multiplied by 1 plus this. That's right. Get this. You can calculate the feed. Feed equal to vertically required multiplied by 1 plus excess. This means feed is 0.21 N2 NO. That's right. N0. Sorry. Equal to 1 plus excess. Excess is 50%. It means 0.5. 1.5 multiplied by vertically required. That's right. Vertically required is 350, and then you can solve for N0 for this case. Right. Okay. For this case, the first step, you use the 50% excess, and then you can calculate feed of air. That's right. This is N0 is the amount of feed air. 2005 less mole air feed. In the second step, you consider like the 90% excess, 90% ethane conversion. 90% ethane conversion means 10% unreact. 10% unreact means ethane is 10% of feed. Right? Of feed. Feed is 100. N1 is equal to 0.1 multiplied by 100. You get N1 equal to 0.1 multiplied by 100 mole ethane in feed. You get the unreacted ethane is 10 mole. Easy for this case because you know, right? Feed is 100, but it react to be the product is 90 and unreact is 10%. This means 10 mole is unreact. Then you can calculate the amount of ethane react is 90 mole. Okay. For the third information is 25% convert to CO. Convert to CO. For this case, 90% ethane conversion is equal to 90 mole ethane react or convert. From this, from 90, 20% of 90 is convert to CO. For this case, from 90, okay. And then you can calculate N4. N4 is mole of CO generate amount of CO produced during the reaction. For this case, you can back to the chemical reaction or CO. 2 mole CO produced based on 1 mole ethane react. This 1 mole ethane react generate 2 mole CO. But for this case, we react ethane to the CO is 0.25 multiplied by 100 multiplied by 90. Because it's 25% of 90 is convert to CO. 25% is 0.25 multiplied by 90. This amount of ethane react to CO. Okay? This mole also cancel. And so you get mole of CO generate equal to 45 mole CO. Okay. For this three information, you can solve for N0, can solve for N1, and you can solve for N4. Right? And the next step, you have to balance, right, on the nitrogen balance first, because nitrogen is inert. There is no reaction. Okay. Input minus output. Generation, consumption equal to accumulation. For this case, no generation, no consumption, no accumulation, because we have the initial step and final step, or input and output continually. Okay, for nitrogen is input equal to output. The input nitrogen is 0.979 multiplied by amount of air feed, like 2000, and finally is amount of air feed, or N0. In air includes 29% nitrogen. You can calculate nitrogen. And the next one, you balance based on atomic balance. We have 3 carbon, hydrogen, and oxygen. For atomic balance, I talked you already, based on the mass conservation. There is no generation, no consumption. But for this case, we consider it the initially and the finally. Initially, the chemical react, and then you get the product. You feed and output, the air feed and output for control. For this case, atomic balance input equal to output. Okay, the first step, you balance based on carbon. Back to the chart. The carbon, about carbon input. The carbon input based on ethane. We have only one term of carbon input. About output in ethane, output in CO, and output in CO2. We have 3 output. Carbon, 1 input and 3 output. Okay. Carbon. About carbon input. The carbon input in methane. This is based on the feed methane. This is based on the chemical reaction. You have to back to the chemical reaction. You know, right, for the methane, the first methane from the chemical reaction of methane. In terms of methane, sorry. 1 mole ethane include 2 mole carbon. Good 2 mole carbon, but for this case, we feed 100 mole ethane. Okay, when ethane is cancelled, until you get 200 mole carbon input. About output, we have 3 terms of output. Output in ethane is N1. N4 is CO and N5 is CO2. The first term output in terms of methane. You know, is 1 mole methane include 2 mole carbon. The ethane output is N1. But the second term, carbon output in terms of CO. You know, 1 mole CO include 1 mole carbon. Mole of CO in the output is N4. For this case, you know N4 from the previous slide. The last term is carbon based on CO2. You know, 1 mole CO2 includes 1 mole carbon. But for this case, the N5 mole of CO, mole CO cancel. You get mole of carbon. For this case, you know N1, you know N4 from previous slide. You can calculate N5 directly. For the carbon balance, you can solve for N5. And the next step, you balance based on hydrogen balance. How about hydrogen input output? Hydrogen input in ethane, only one. Output in ethane and in water, we have two output term, one input term and two output term. Input based on ethane, 1 mole ethane. That's right. This 1 mole ethane includes 6 mole atom hydrogen. And for this case, we feed 100 mole ethane and then mole hydrogen. The output we have two terms. The output of hydrogen output with ethane. From 1 mole ethane includes 6 mole of atomic hydrogen. And for this case, the output of ethane is N1. N1 equal to N. That's right. The second term is water. 1 mole water includes 2 mole atomic hydrogen. But for this case, the mole of water output is N6. For this equation, the unknown is N6, and then you can solve for unknown N6. And the last balance based on oxygen. Oxygen, you back to the foot. Oxygen input in air, that's right, in terms of gas oxygen. And oxygen output into oxygen, N4 carbon monoxide, N5 carbon monoxide, and N6 water. We have 4 terms of output, 1 term of input. First step, oxygen input based on gas oxygen 1 mole include 2 mole atomic oxygen. How about oxygen input? Gas oxygen input is 0.21 multiplied by N0. How about N0? N0 is 2,500. That's right. You multiply 0.21 with 2,500, you get amount of oxygen. This is amount of oxygen. And oxygen output from 1 mole oxygen include 2 mole of atomic hydrogen. Oxygen output is N2. This is unknown now. And CO, 1 mole CO include 1 mole atomic oxygen. CO, about CO. CO is N4. N4 is 45. Right? It's 45 CO. This is, if you remember that you can cancel mole O2, you get mole oxygen, mole carbon monoxide, you get. For the third term of output based on CO2, 1 mole CO2 include 2 mole atomic oxygen. And for this case, CO2 is N5. N5 is 133. 35, that's right. It's 135. It's mole CO2. Mole CO2, you get mole atomic oxygen. And the last term based on water. 1 mole water include 1 mole atomic oxygen. Water is N6. That's right. Water is N6. N6 equal to 270 mole oxygen on water. All of 5 terms. This is unit of mole oxygen. And then you can solve for N2. You get N2 right. And then you analyze it the gas. That's right. Summarize N1, N2, N3, N4, N5. This is based on dry gas. Total is 2,396 mole dry gas. If you plug N6 is water, this is a total mole with wet basis. And then you can calculate the composition based on dry basis. If you calculate based on dry basis, you only consider N1 to N5. And then the fraction of ethane is 10 divided by total dry gas, get this. And oxygen is divided by the dry gas, you get this. This is based on dry basis. And the last one, you calculate the ratio of water per dry gas. And use this ratio to convert from dry base heat to. Okay. For this case, I talk to you the example about the material balance on the combustion reaction. For this case, the reaction is multiple reaction. The atomic balance is preferred. For the last example for the combustion reaction, this case we don't know what is the fuel with the fuel. We know only the hydrocarbon gas is burned with air. The dry base heat produce gas composition of 1.5 mole CO, 6.0% CO2, 8.2 CO, and 84.3 nitrogen. Okay. And then there is no atomic oxygen in the fuel. Right. For this case, the fuel is no atomic hydrogen. They are all carbon and hydrogen. Calculate the ratio of hydrogen to carbon in the fuel gas. Right. Calculate on what will might be. Then calculate the percent exit air feed to rate. For this case, the question is what the kind of food for this case. You don't know kind of food. Okay, and then you know the composition of the stacked gas in based on dry basis. For this case, we can base it based on 100 mole product gas because you know the composition of product. Okay. 100 mole is the mole of dry gas. Okay, and then you draw the flow chart. The 100 mole dry gas include to 0.015 CO, 0.06 CO2, 0.08 O2, and 0.843 nitrogen. This is the fraction of the product. And also NW is water. We don't know water. How about the feed? We have two feed. That's right. Feed it is full. You don't know composition, but you know only the C and hydrogen. No oxygen. Okay. NC is amount of carbon or mole of carbon. N is amount of hydrogen or mole of hydrogen. And the second feed is air. That's right. Na is air. Air includes 0.21 mole oxygen per total mole and 0.79 mole nitrogen per total mole. Okay. And the next one, you write the chemical reaction. For this case, you can get the first step. Okay, carbon react with oxygen, you get CO2. Carbon react with oxygen, you get CO. For this case, it's incomplete reaction. Right? And hydrogen react with oxygen, you get water. These three reactions possible. These are possible. For this example, we don't know what kind of reactant. You know, only carbon, hydrogen react with oxygen. These three chemical reaction is possible. Okay. For this case, you analyze the degree of freedom analysis based on atomic balance. We have four unknown: NC, NS, NA, and NW. Right? And we have three atomic balance: CSO, and one inert is. Right? Okay, for this case, you get 0 degree of freedom. You can balance this. Okay. You have no, another information. That's why the first step you balance based on nitrogen balance. Nitrogen is inert. For this case is input output continuous. You get no accumulation. Input equal to output. Nitrogen input is 0.79 multiplied by Na. Right? Equal to 100 multiplied by 0.843. You get Na. This case. But you know output nitrogen. But you don't know input. But input you know composition is 0.79 multiplied by Na equal to 0.843 multiplied by 100. Then you can solve for Na. This based on 100 mole dry gas. Next step, the balance based on atomic balance. Atomic balance I talked to you previously, so it's the same. There's no generation, no consumption, but for this system, input equal to output. There is continuity for output. And no accumulation, you can input equal to carbon balance. Carbon balance for input carbon, we have only NC. And output based on CO, based on CO2, we have two output. Okay. NC input carbon input based on CO. For CO, 1 mole CO include 1 mole carbon. How about CO output? CO output equal to 100 mole dry gas multiplied by fraction of CO. Fraction of CO is 0.015 mole CO per mole dry. Mole dry gas, mole dry gas, mole CO, you get mole carbon. The second one, carbon in CO2. That's right. Carbon in CO2. 1 mole CO2 include 1 mole C multiplied by amount of CO in output. This is 0.06 mole CO per total mole dry gas multiplied by 100 mole dry gas, you get mole C. And then for this case, you can solve for NC. NC is 7.5 mole carbon. And also, for next step, oxygen balance. Oxygen balance input based on O2, output based on CO, CO2, and oxygen. Okay, input CO include right 0.21 Na. 0.21 Na is the mole of gas oxygen input. 0.21 mole oxygen per mole air multiply Na is mole air, you get mole oxygen. Mole oxygen is 0.21 multiplied by Na. Multiplied by 2. What is 2? 2 is 2 mole atomic oxygen divided by 1 mole gas oxygen. Okay, equal to water, CO, CO2, and oxygen. Okay, we have 4 terms for oxygen. In CO, CO2, oxygen, and water. First term is water. NW is mole of water output. 1 is 1 mole atomic oxygen per 1 mole water. Right? And the second term, this is based on CO. CO. 1 is 1 mole atomic oxygen per 1 mole CO. Mole CO output. CO output is 100 multiplied 0.015. This is mole CO output. The third term is CO2. That's right. 2. What is 2? 2 means is 2 mole atomic oxygen from 1 mole CO2. 0.06. 0.06 is 0.06 multiplied by 100. This is amount of CO2 output. And this based on O2. That's right. 0.082 multiplied by 100 is amount of O2 output. And all you need is mole oxygen. The unknown only NW. You calculate for NW. And then you balance on hydrogen. Hydrogen input is NS, output in water. Only 2 terms. Hydrogen input NS. Hydrogen output based on water. 2 mean 2 mole atomic hydrogen from 1 mole hydrogen, 1 mole water. Then you can solve for NW because you know NS already. You know NW already from this. And you can solve for NS. Now you know NC, you know NS. And then you calculate the ratio of NS NC. NS is 29. NC is 7.5. You get about 3.797 or about 4. That's right. You can get like it should be methane because it's 4 mole hydrogen per 1 mole carbon. It's mostly it's maybe ethane or methane for that case. For this case, you can conclude that the fuel is methane. For this case, you can get this methane because it's 1 mole C and 4 mole hydrogen. And also then you calculate the percent excess air. Percent excess air from the combustion percent excess you have to calculate based on complete combustion. Complete combustion. The theoretical oxygen based on two of these reactions. Assign two of these reactions. A 1 mole carbon from 1 mole oxygen, and you feed 7.5 mole carbon. Right? And 4 mole hydrogen. Right? Include 1 mole oxygen, and you know mole of hydrogen for it. Okay. The theoretical require is 14.95 mole oxygen. And then you can calculate feed oxygen is like this. Feed oxygen, what is feed oxygen? Feed oxygen is 0.21 multiplied by Na. It is 22.4 mole oxygen. And then you can calculate percent excess is oxygen feed. Oxygen required theoretically, and then you can solve for percent excess is 49.8% excess. Okay. For this case, the example 3 and example 4, I talked to you about the example for the material balance and the combustion reaction. For this case, I talked to you about 4 or 5 weeks about the material balance. First, we talk about the general material balance on the integral balance, differential balance, and also in the batch process, continuous process, something like this. But mostly we talk in no accumulation term, right? No accumulation term. And we balance based on the no reaction and reaction system, balance based on single unit and multiple unit. And then I think you can use this, and you can to try to practice a lot, because when you find the material balance, when you work in the industry, it helps you a lot to calculate the material balance of our process, and you can solve the problem. You can find the benefit for your company or the profit, something like this. And moreover, there is not only the material balance in the process. You have to include more balance based on energy balance. We will talk about to this later. Okay. See you for the next lecture. Thank you.